Okay, so Chem 124, we're looking at a problem from homework 4, and it's number 6 where we're looking at a couple different crystal structures. We're talking about how the crystal structures change when we turn the oxygens into seleniums and what that looks like. I have trouble seeing it in the two-dimensional representation of a three-dimensional thing. So let's try doing the Z diagrams for both of these structures. This will give us practice with Z diagrams, and it'll also, can I look at that?
Yeah.
It'll also help us hopefully understand what's going on. So this would be for the first one. This is the cadmium oxide, where the oxygens, I'm drawing them in black, make a face-centered cubic. And I only need to do the 2, but I'll do the Z equals 0, 1/2, and I'll do the 1 as well. But normally we just say the 0 and the 1 should be the same if we're making a repeating structure. Right, so we've got those, and then I'll go ahead and do the other, the cadmiums in green. And then we've got this. This is for cadmium oxide, which is the same. It actually has the same structure as the sodium chloride. So if you just go back to the worksheet we've been working on, this one's not so bad. I can look at this green dot, and we do have to think three-dimensionally. So I've got 1, 2, 3, 4 nearest neighbors in this plane, and then I've got 1 above and 1 below. I don't know if any of you've played three-dimensional chess before, but it's just, or checkers, just thinking like that. So this is going to have 6 nearest neighbors, and if I do the same thing with this black dot, 1, 2, 3, 4, 1 above, and then I can go to the Z minus 1/2, the next one below it. Because remember, this is just the simplest structure. We can still expand this infinitely in three-dimensional space. Let's go ahead and look at, so both of these, the cadmiums and the oxygens, both have a coordination number of 6. Because this is an ionic solid, we know that the positively charged thing is going to be closest to the negatively charged thing. So the cadmiums, the green dots, will be next to the black dots, the oxygens. And I'll do a little color coding here. I'll underline the cadmium in green. I'll underline the oxygen in black. Now let's go ahead and see if doing the same thing for the cadmium selenide gives us the same insight. And I have to look, because this has a weird number of layers. This one's a bit different. I've got 1, 2, 3, 4, 5 layers on this one. So when I draw this, I'm going to do 1, 2, 3, 4, 5 boxes. I'm going to start with the negatively charged thing, which is not going to be too bad. It is just like oxygen. It is going to be a face-centered cubic. So this is my Z equals 0, 1/2, and 1. With this being like a 1/4 and this being 3/4. Right? So notice I can evenly split the structure up into different layers, and I'm just going up. Since I've got 5 layers, I've got 5 things counting up to 1 using 0.
Can you show me how the layers
Ooh.
in it a little bit more?
Yeah. So if you do have this picture in front of you, take a look on the computer screen or that screen. So what I did was I essentially looked at the middle of each atom. I don't know if you can see that on there. So look up this picture. So bottom layer and top layer is a great place to start, right? And then I just want to look, where do I have atoms that line up in the same plane? And I can see that the seleniums make their own plane, and then I've got two planes of cadmium kind of halfway in between those. So I can pretty much, if I ignore the 1/4, 3/4, I can do a face-centered cubic Sorry, I just did the wrong thing. Let's fix that. I can do a face-centered cubic just looking at the selenium. And then I have to say, okay, I've got to fit another thing in there, and it's going to fit halfway in between this layer and halfway in between this layer. Right? And so that's kind of how I think about it, is I do the one that's obvious for me to see, and then I go in and fill in the inside. I could have done the same thing with this, where this one was a bit easier because if I look at it, the centers of the oxygens and the cadmiums in the first one, the center of the atoms all line up on the same plane. This one, they're offset. So I have to do this offset. And I'll do my cadmiums. I'll do cadmiums in green again, since I already have cadmiums in green. In this case, I've got a cadmium that's kind of at this front corner, but not actually on the corner. One that's at this back corner. And then I've got the opposite thing here. Front corner, back corner. That really doesn't help me see nearest neighbors too well. Actually, now that I'm doing it, I'm like, oh, that didn't help me. Because the way that I have to think three-dimensionally, well, depending on how good you are at visualizing this in 3 dimensions, like this 2-dimensional, 3-dimensional connection, maybe you can. Because if I look at this dot, there's nothing next to it in this plane, but if I look at the plane below it and the plane above it, I've got these 2 dots and these 2 dots kind of making a sandwich around it. And if we, again, look at the picture, looking at the cadmium that's labeled cadmium, and I just consider the seleniums next to it, I can now, like with this 2-dimensional picture and this 2-dimensional representation, between the Z diagram and the 3D representation, I can kind of see that, yeah, these 2 are above it and nearest neighbors, and these 2 are below it and nearest neighbors, which would give me a coordination number of 4. Right, so that's how I can kind of see that. Now I also have to do that with the selenium, which is challenging. But again, if I try to look at the extra dimensionality, like if I look at this dot, I can see that I've got these 2 above it, and I would also have 2 more below it. So the coordination number would also be 4. And that makes sense to us. That makes sense to us because of what the molecular formula is, right? And this is actually this idea of coordination number from doing crystal structures and using X-ray diffraction to determine crystal structures is part of how we can figure out the molecular formula or the empirical formula of something. I see coordination number 4, coordination number 4. The lowest ratio is 1:1. So this is part of the power of doing crystal structures, is it can get us actual structural information about the chemicals and how the chemicals are interacting with each other. And in case you're like, yeah, that's great, but how many salts do you care about? We can do crystal structures of DNA. We can do crystal structures of proteins. We can do, there's a really exciting field, I don't know how many of you are doing material engineering, but there's a really exciting field of like new metals and new like alloys that are looking at crystal structures, and they're looking at very complicated crystal structures because they're doing things where you essentially have this crystal structure, but you replace one selenium with one oxygen and see how that changes all the physical properties. And we're talking like 1 out of like 200 are changed, and it has this actual surprising effect on the physical properties. So, let's move out of the way. We're going to need to get Jaminda her seat back.
Oh, sorry.
Yeah. So that is, did that help? Great. Okay. Other 124 questions. I'll get to them a little bit. Other 124 questions.
How much of homework 4 is on the midterm?
How much of homework 4 is on the midterm? Great question. if I remember correctly, up to number 12. Up to number 12.
Okay.
So like the first half of homework 4.
Alright.
Yeah.
Could you very quickly just draw the Z diagrams for the body centers that and like the rest of them?
Can you draw them and I'll tell you if you're right or not?
Yeah.
Cool.
Can we do number 7? Talking about zinc selenide.
What does that one ask?
It's talking about I need help with volume of unit cell and edge length of unit cell.
Ah, ooh, that one's tricky. Okay,
Because I
so-
feel like it doesn't give enough information and I don't know how to.
so in order to use zinc selenide,
Thank you.
I'm just going to go ahead and relabel this. Right, so it turns out zinc selenide takes on the zinc blend, which was the same thing we had in problem 6, where the zincs are the green dots, they're the ones inside the unit cell,
Yes.
and the selenide are the blue dots. And whew, we have to find some way that we have complete connectivity. Did I forget a dot in the middle here? No, this is, no, okay. I was thinking of the previous structure. Okay, so it's asking about edge length. That's tricky. That's tricky. So, we're going to have to use some trigonometry to figure it out. So, the first 2 problems are okay though, because if I remember correctly, the first 2.
It's how many zinc and how many selenide atoms.
So we've
mass
got our
of unit cell.
counting problem, then we've got our mass. You can see that it's going to get density, right? So we have to figure out how we look at the edge length of this thing, and this is going to be tricky. We can't go across this side because the selenides in this case don't touch. We can't just go across the face because these selenides don't quite touch, if I remember correctly. Can I look at the picture again? The problem, and again, part of the problem with this particular picture is it is trying to give us, so this is not the space filling model, this is just the 3-dimensional, like, it's a cartoon. It's a cartoon to give us an idea. So I feel like this is not necessarily the best picture to try and determine this. So here's what I'm thinking about. Based on the way the structure looks, it looks like I could do a line that goes up and then back down. And that would give us essentially, would this work? If I did a triangle, now that's not going to give us any right angles. So this would give us, this would give us this like half of the middle, but it doesn't give us a right triangle. So the question, I think I'm going to make an approximation here. And hope there's 2 approximations. Do we want to make the easy approximation or the hard approximation? If we make the easy approximation, we say, look, I realize that across the face, for the face center cubic of the selenium, it's not exactly perfect because those zinc atoms, those zinc ions are going to push it a bit. But it's going to be approximately correct. And I can just use face center cubic selenium to say that's essentially going to be the side length. So option 1, approximation 1, which is the easy approximation but probably introduces more error, would say the face center cubic of the selenium, I almost put S minus, that's not a 2. The face center cubic of the selenium 2 minus is approximately the unit cell. That's approximately the unit cell size. I'm willing to bet that's a pretty good approximation. we might be introducing as much as 10 or 15% error though, which is not actually that good. So then we have to say, okay, what other kind of approximation can we make? And the other approximation, just when I look at the picture, I can imagine essentially another selenium fitting in the middle there, right? Wait, can I look at the picture again? I have to see if this approximation is going to work or not. So essentially what I'm trying to do is finding some way I can make a right triangle on this thing. I haven't done trigonometry in a while. Oh, we can cheat with the picture that I made. It's kind of a silly way to do it. But this should work. This should work. Depending on how much trig we want to do. So forget approximation 2. Approximation 2 is not actually going to be valid with this faking like there's an atom in the middle. I think the other thing to do is to just say, we know these lengths. This is going to be radius of selenium, radius of zinc, radius of zinc, radius of selenium. And you look at it and say, yeah, but you don't have a right triangle. And then this would be getting us essentially this line here. That dotted line would be this dotted line there, right? So it would get us some funny angle. But then we could say is the same there, and we could drop the diagonal there, right? So we have to do essentially 2 weird triangles in order to make this work. How well do you remember trigonometry? Is everything I'm doing okay so far? I don't think I would, would I put this on? I was about to say I don't think I would put this on the test, but I've definitely put a problem like this on the test in the past. And I've definitely done something like this on the final. So, it wasn't quite this complicated, but it was this same kind of like, oh, you've got to show that you can kind of think about this and approximate things. So we can essentially drop a triangle there, and we can use that to get that length. And then we can relate, can we relate these 2 triangles? We'll be able to relate those 2 triangles, I believe. Trigonometry, right? Because we're going to be able to figure out this length, we're going to be able to figure out this length, and that's going to allow us to figure out the length of that side. It's a lot of trigonometry. It's kind of a hassle. Approximation 1 is probably going to be pretty close. But we could do this, right? The other thing we could do is we could figure out the angles of these triangles approximately, and we could just use like sine-cosine relationships and not have to do like 5 different Pythagorean theorems to get it. It's interesting. Have you tried looking up zinc blend side length and seeing what it spits out? Another option, right? Because at this point I'm like, ooh, I don't want to do the wrong thing, especially since I'm recording this video. So I would actually, let's do it real quick and see what kind of ideas we get.
If you use the face-centered cubic side, what would you use for R?
So if we're using the face-centered cubic approximation, we would just be using selenium. First link, how to determine lattice parameters of zinc blend. It's also on physics forum.
What?
So first links.
Yeah, I'm watching his office hours again.
I'm watching my office hours while you're in office hours.
No. I'm getting him the views.
Wait, Josie. Did you do homework number 313 and homework 4 number 4?
I'm doing number 3 right now. It's on the after hours.
That is a terrible answer. Sorry, I was just looking to see if there's a quick
Oh,
answer.
so do you?
Yeah.
The-
It's like, wow.
The answers on here are not
Number 4,
encouraging.
which one?
Number 4.
Number 4. Oh, homework 4. Number 4.
This one looks pretty neat.
Oh, I know how to do it. It's the same exact thing as number 13 on homework 3.
Oh, 3 root 2. Oh, that's interesting.
It's
So-
literally the same thing.
They're essentially saying that you can do a face-centered cubic and just take into account that you have this like averaged radius. So they're using a different approximation of the face-centered cubic. So rather than just using the zinc blend distance, they're essentially saying you can, because if we had the face-centered cubic, you would have across the face, you'd have these 3 touching, and that would be your side, right?
Yeah.
And what they're saying is, oh no, you've got a gap created. You've got a gap created by this, by that zinc that's inside there. And apparently they're saying you can just solve for how that zinc adds a little bit of distance. But they're just saying, I don't agree with I don't think they're actually doing it like correctly. They're just making another approximation, at least in the first 3 links I looked at. And they're saying, oh, you just take the average of this radius and that radius and say that you've got an average atomic radius. But like that's clearly not an average. You actually have to solve the triangulation in order to get like, but they are suggesting a different triangle than I suggested, which is to say, actually no they're not, they're just doing it in a different direction. But essentially if you looked at the bottom triangle I drew, if you can solve this L here, which is my dotted line, that L is going to be essentially your face length. And then that face length becomes what you use for the face-centered cubic radius rather than the exact radius, like rather than just the selenium radius. It's a little tricky. So I would call this quarter side. That's a quarter. Oh, that looks terrible. Yeah, that would be tricky. I think it's possible. I just don't feel like doing it right now. Do you want me to keep doing it? Okay. Because I think I could. That length is going to be a quarter of the diagonal. I would relate that. Well, now I want to do. Let's not. Let's move on. It's not going to be on the midterm.
Okay.
Maybe by the final we'll need to figure that out.
Okay.
But it won't be on the midterm.
Okay.
Other questions from 124? Hey, yeah.
Can you explain the Lewis-Scott symbols?
Don't worry
Don't
about
worry
those.
about
We
it?
haven't done that yet.
Okay.
That
That's
won't be
number
on the midterm.
9, so just
That's
don't-
part of number 9.
Yeah.
Yeah.
You should be able to do the other part of number 9, which is asking for the electron
Yeah.
configurations.
Yes.
Oh yeah.
So you should be able to do the electron configurations and predict the charges, and then predict the.
And the charges just based on how those two are related
Yeah.
to each other.
Yeah.
Like that.
But don't worry about the Lewis-Scott part. You should be able to do everything else of problem 9 does.
Okay. And then 10, it says for each ionic compound formula, identify the main group to which X belongs. 10C.
This is a great problem.
XCO3. How do you
Oh, yeah.
account for the CO3?
So, again, is that the last one?
Yeah. The other two I got, but
The other 2 are fair. The last one is not quite fair.
okay.
But of course, if I told you that CO3 has a 2- charge, you could figure it out.
Oh. Is that a polyatomic ion? Yeah, okay.
It's time to start learning the common polyatomic ions. So carbonate's a common polyatomic ion. It has a charge of -2, and then the problem becomes very easy. If you didn't realize that it was a common polyatomic ion, then
Yeah.
you're feeling really stuck, right? You can recognize the fact that oxygen has a -2 for each, and we've got 3 of them. That's not times 6, that's times 3. That's going to give us a -6. And then we have to say, okay, what was the charge of carbon going to be? And there's no way you can figure it out just by, I mean, based on the periodic trends, you could kind of figure it out. But this is not an ionic bond, so just looking at the charges isn't, just looking at the electronegativity isn't going to tell us the charge on carbon. And we're going to learn how to do this idea of formal charge, and we're going to learn how to tell what the Lewis structure for this is, but that's after the midterm. So if I put like a hint, so if I did something with a polyatomic ion on this midterm, I'd have to do like, hint, this is a common polyatomic ion with charge blah.
Okay.
And then it'd be easy.
Okay.
Phosphate has a charge of -3. Question?
Yeah, I had a question. So, I was going over last night. What was the? I don't know why I couldn't read these together. I think it was too late. But it was like, what is ionization energy and electron affinity have to do with electronegativity? Like, how do they relate?
Oh, yeah. So remember, if we draw a quick periodic table, we can look at ionization energy. Where's ionization energy smallest? Down here.
Down, yeah.
And then it gets bigger as we go that way. Electron affinity, where's electron affinity the smallest?
Same place.
Same place. Also goes that way. Ionization energy is the energy to lose an electron. Electron affinity is gain an electron. Right, and so we can look at these two things and look at how they compete with each other or how they help each other. So when I look at this bottom corner, I've got something that is going to lose an electron easily and not gain an electron easily. And I should mention these are kind of opposites of each other, right? Ionization energy is a positive energy that you have to put in. That's an input energy. And then electron affinity, the energy of gaining an electron, that's an output energy. And it's something when an electron is attracted, energy is released. The same way that when an electron goes from a higher energy level to a lower energy level, energy is released. So this is an energy release. So the fact that they're both small means you get a very little amount of energy released when you gain an electron, and you have to input a very little amount of energy to get rid of that electron. These two things combine, essentially, and tell us when I've got two, and remember, ionization energy, electron affinity, these are for the single atoms by themselves, and just hitting them with energy and seeing the electrons get knocked off. When we look at electron affinity, we're looking at if I put two atoms next to each other, how do they interact with each other? Which one's more likely to attract an electron away from the other? So when we look at electronegativity, we end up having something that kind of points the same way. So atoms near each other stealing electrons. So this is what gives rise to, this is one explanation for ionic bonds. If I've got a sodium next to a chlorine, I've got something that's likely to steal electrons next to something that's not likely to steal electrons. So chlorine will essentially coulombically attract, it's going to be that, it's going to be a combination of the Coulomb force of just the positive charge of the chlorine nucleus attracting the electron. Is going to be the quantum mechanics as well of the energy of losing that electron from the S shell in sodium and the energy gained from the chlorine filling its P shell. That energetic benefit makes it so we'd see Cl- and Na+. In all reality, we've already got sodium ions floating around everywhere and chlorine ions floating around everywhere, and they just combine. It's not like in order to make salt you need sodium metal and chlorine atoms and put them together.
Yeah.
And that has to do with the fact that we need to think about the total environment that something's in, right? Sodium metal, if I had a chunk of sodium metal and I just left it out in the room, it's going to react with the water in the air, it's going to react with the oxygen in the air. It's just going to sit there and react away and become sodium ions and like sodium oxide or sodium hydroxide, or depending on what it's reacting with.
Okay, for sure.
So anything that's got a significantly larger electronegativity, then it will react with it. And this starts to explain some of the reactivity that we're going to be looking at after the midterm. So these two ideas kind of combine to define electronegativity, but we almost always just go to electronegativity to find reactivity, because that's when you're looking at two things interacting with each other.
This is just a quick question, but how would the valence electrons look for Cu plus, for copper plus?
Copper plus. So copper plus, let's go ahead, let's start with just doing copper. What's the electron configuration for just copper? I'd need a periodic table.
Yeah.
Where's copper on that periodic table? No, you tell me.
So 3D
What's the noble gas before?
Argon.
argon.
So we're going to do argon. And just to be clear, we're doing the ground state electron configuration, right? We're doing the lowest energy possible. So we're going to have a 4s2, 3d9. And we're going to look at that and say, okay, is this actually the lowest energy configuration? This is based on everything we did with hydrogen and the hydrogen-like orbitals. This is what we would write. But it turns out when we actually look at the energetic interactions of these electrons, we've got something that's going to be a lower energy interaction to define the ground state. We're going to get that 4s1, 3d10.
That's because it's a metal, right?
That's one of the, so there were 5 exceptions that I was like, hey, we should remember these 5 exceptions for the transition metals. And it was the 3 that were in the D9, copper, silver, gold, and then the 2 in the D4, which, oh, can I remember what's in the D4? Chromium, is it chromium?
Yeah, chromium and
What's below chromium?
MO.
Molybdenum, right? Those are not the only exceptions. There's a lot of exceptions because all of this is actually done from an energetic argument. And this is also just the ground state configuration, right? Can we have excited state configurations? Someone asked the question, I was like, oh, I wish that was on the midterm. Someone asked the question of, I think it was on a worksheet. So it was which hydrogen, it was something along the lines of which hydrogen atom would have the largest radius. And it was like a 1s, 2s, 2p, 3s, 3d. Or, sorry, 3p, 3d. And they were like, well, can hydrogen even have a 3p? Yeah, it's just not the ground state, right? We can always, and that it's very important that hydrogen can have a 3p because that's what we did when we were doing the emission spectroscopy. We were exciting hydrogen from the n equals 1 to the n equals 3, and then seeing the n equals 3 relax to the n equals 2 before it relaxes to the n equals 1. And in fact, because we were exciting billions and billions of atoms, we were seeing dozens of different excitations and relaxations, but only a few of them were actually visible. So again, this is just a ground state configuration.
3p would be the biggest though, right?
What's that?
3p would be the biggest radius though, right?
Yeah. 3p would be the biggest in this case. They thought 3d, and I was like, oh, remember, d gets smaller. So this is copper plus. Then this is copper. And for me, whenever I'm doing the charged ions, I still do the uncharged so I can get the look at it, because this electron configuration tells me why the copper plus is a common version of copper that we see. Which electron am I going to lose? Yeah. So we're going to just have 3d10. That would be the copper plus. Some people like to put the 4s0 in there. I find it to be kind of redundant information. If I don't write it, of course, there's nothing there. It does show you where the electron was lost from, but it's not there, right? Now the funny part is, for copper, this is less true for, again, because this is energetic arguments for everything. When we're looking at copper, it turns out this energy benefit of moving the electron, it's actually a pretty small benefit.
Oh, really?
Yeah. And it turns out it's such a small benefit that in the natural world, when this is next to things that have a significant electronegativity, we also get copper 2+ in a lot of cases, which is going to be argon 3d9. Because the energy benefit here in like losing that electron is actually reasonable. Again, it depends on what it's in contact with. Both of these forms of copper are pretty common in the world, or both of these oxidation states. Remember when we talk about charge, we can call it oxidation states. This would be Cu2O, this would be CuO, copper oxides.
Okay.
But both of them are common in the world because the energy benefit of this change up here is relatively small. Right? When we go to things like silver and gold, silver pretty much is always in the +1 state because the energy benefit is much more significant.
Okay, so it's kind of it's molecule to molecule or element to element, I guess.
Yeah, right. All of this should be, for all of these, we should actually look at the experimental observations or the pure quantum mechanical calculations to figure out what's going on with them.
Why do they all go to the d orbital?
Why do they all go to the d orbital? What's going to give a stronger interaction between electrons and nucleus? What are the two things? Coulomb force.
Oh, smaller radius.
Charge, smaller radius. Which has the smaller radius? The d. So actually going to the d orbital gives a stronger interaction with the nucleus, which will essentially reduce the energy. So it's kind of a weird thing to think about. And again, that's a very hand-wavy kind of like, oh, good approximation-ish kind of way to argue about it. But again, it's the energetics. And again, we're just looking at ground state configurations. When you start to melt copper, when you start heating it up to melt it, the electrons are all getting excited. That's part of why it starts, well, it's part of why it starts slow, but like, you're exciting the electrons, you're going to non-ground states.
Got it.
Question in the hallway and then over here.
So for number 7 on homework 4, it has the unit cell of zinc oxide, but it's the same thing as zinc selenide. And I was wondering for B, how to find the mass of the unit cell. Because you know how to find the volume of the unit cell.
Okay.
The volume equation, but
Yeah.
you can find the mass.
So to find the mass, this is for zinc.
Zinc selenide.
So to find the mass of zinc selenide, you need to identify the number of zinc atoms, the number of selenide atoms, and then do the zinc atom number times the mass of zinc, plus the selenide number, atom number, times the mass of selenide. We did part of that problem earlier, but we didn't do that part of the problem. Should we do that part of the problem real quick?
Yeah.
Okay. Yeah. So, if we look at, we're looking at zinc selenide, right? So I'm going to go ahead and draw this real quick. I'm going to draw the short version. I use green again. We get something like this, right? I think I remembered everything. This is the Z diagram for it. Oh, right, yeah. These gotta flip.
Said 5 layers.
What's that?
We got the fifth
The
layer.
same as the first.
Fifth layer is the same as the first layer, right? So this is my shortcut. I'm just gonna say, look, my 0 layer and my 5th layer are gonna be the same. That's part of what defines the unit cell. This is gonna be a 1/4. 1/2, 3/4, and then the one layer is going to look the same. So this is my shortcut. If I counted the number of atoms, so to do, if I remember correctly, the selenides are the ones I put in black. The zincs are the ones I put in green. The selenides are in a simple face-centered cubic. Oh, sorry, I didn't get to your question. They're going to be a simple face-centered cubic. How many atoms in a face-centered cubic? 4. So I'm going to have 4 seleniums times the mass of selenium. So I'd have to look at the mass of selenium. Then I'm going to go ahead. Notice these zincs are completely contained within the unit cell. So I'm going to have 4 zincs times the mass of zinc. Go ahead, do me a favor, get out your calculators, get out your periodic tables, and calculate that real quick.
I have a question. So why is it 4 zinc and not 8?
That's just the crystal structure. Right, so if I look at this, how many green dots do I have? 4. And they're all like inside the unit cell, they're not getting chopped at all.
For
Oh, for selenium,
Yeah.
we have to remember that the corners, anything that's on an edge is going to get cut. So all of these are cut in half. So this only counts as 1, 2 atoms. All of the corners, and remember I've got 2 of these layers, all of the corners only count as an 1/8. So that's 4/8 plus 4/8, and then that's going to be 1/2 plus 1/2. So that's going to be 1, 2, 3, 4. Yeah.
And like line with that. So for the side-centered one, it'd be 1 atom, and then for the bottom, it'd be what?
The side-centered?
Side-centered.
Simple cubic, simple cubic. Yeah.
Yeah.
I was thinking of the, so when you said side-centered,
Yeah.
I was thinking of the rock salt structure,
Yeah.
which has ones that are on the
Okay.
center of the edges.
For the simple cube, it'd be 1, and then for the body-centered, it would be 2.
Yep, that's correct. Come in more. Do that calculation. I want to see if that person with the 129 question ran away.
You did.
Totally not.
Yeah, but I have a question.
Yeah, what's up?
Um,
All of 124 people, find another question that you all want me to work on.
I don't understand number 9.
We haven't done buffers yet.
Oh, cool. Okay, I have another one.
So anything that mentions buffers is not going to be on there.
It's right
We
there.
already got buffer calculations.
Okay. So after 9, or I didn't understand this one.
That's okay, so because it's our most fruit such as sauerkraut, there's a weak monocritic acid.
Oh, I think I got it. I just wanted to make sure this is.
Which one is it?
It works for my feet. So I found the pH, but no, I found the concentration of the pH and initial.
History.
Ooh,
I don't know.
what?
Who figured out what?
So pH is actually going to be your X value. If you look at this, if you write this out, you know, 0.1, you have -X plus X plus X. X is going to be your H3O plus concentration. That's going to be Ka equals X squared over 0.1. If you look at the problem, it's asking you to find the Ka.
Okay.
Yeah, and so you just try to use a shortcut and you jump too fast.
Okay. So what would I do for this one?
So,
Here it is.
So for this one,
It's okay.
for this one, we're gonna use the same equation we always get.
Like all other questions,
X
where it's like what would be the main group of like
Oh, wait, I did that.
sodium.
Okay.
See it now?
Yeah. Okay.
Something.
So you just
No, it after
equated.
something before.
I'm gonna make it so this doesn't matter as much.
I don't know how.
I can remember.
So what you would do. So what you would do is you would recognize the fact that X is going to be your H3O plus concentration.
Well, you know that CA
Oh, so don't use pH for the first part.
You do, because you need the pH to find the H3O plus concentration.
Okay. So for the H3O1, do I just take the log of pH? Oh, okay.
Negative log, that equation, I don't know what's wrong with the equation sheet on the,
You did. How did you do it?
So,
So like,
So these are the main groups, right?
this is gonna have a 2 plus charge.
Thank you.
So then,
That's handy.
yeah,
Additional pencils. Okay,
for each ionic compound identified.
that makes sense.
which X
Thank you.
Cool. Yeah. Bet.
Since you know that has the 2
Okay, 124.
X's, So 2 times.
Sorry about that brief interlude.
So you would do 1. So
What questions do you have?
Okay, I have, so how much, maybe you can't tell me this, but like, as far as
Just like asking them.
needing to know like the history of the atom and like who figured
No,
out what?
no, no.
None?
I don't ask history questions. I personally find scientific history kind of one of the most fascinating histories there is. A lot of how things were discovered, when things were discovered, who discovered it, and like who simultaneously, like there's a lot of simultaneous discovery. I find scientific history to be one of the most whitewashed histories there is. There was an incredible amount of research across the Middle East centuries before like Europeans, like pretty much all of the scientific glassware we're still using today was originally created in the pre-Persian Empire, but like in where current day Iraq and Iran are, is like where all of the glassware styles that we're actually still using come from. Almost all of our understandings of combustion were first done in Asia. Like fireworks
Yeah.
were all figured out and determined way before anyone in Europe did it. Gunpowder, like it's funny because a lot of Asian cultures were using gunpowder
Way before.
but not for guns. They were using it for like celebrations. And it was Europeans who saw that and was like, I bet I could make things explode big, and turned it into weapons.
Okay.
India did research on dyes and fabrics and textiles centuries before, like hundreds of years before anyone in Europe did it. But for some reason, whenever we learn about this stuff, we all learn about the European scientists that did it. Sorry, yeah.
Quick question.
But no, I'm not gonna test you on that. I just think it's really neat and it's a cool part of history.
The answer to that would be in AMUs.
Yes.
Okay.
Or multiplied by the AMU kg conversion to get it to kilograms.
Or grams. Okay. Yeah.
Question.
Okay, so it's like the mass we have on our curriculum, that's an AMU. So
That's an AMU if you want to do it as mass, or it's numerically equivalent to grams per mole. The number represents both the molar mass and the AMU mass. They're numerically equivalent even though they're conceptually defining different things.
So if you have like a mole of anyone, we weigh that in grams. And then, how did you number that for homework 4? You find the main group for given.
Oh yeah. So let's do one of those. What's part A of that?
I don't have the homework for it.
Homework 10. That was the one where we said.
CaX2.
And it's saying what's the main group of that?
What's the main group of X? So if we look at calcium, can you figure out the charge of calcium?
This is like 4s2.
Not the electron configuration, the charge based on where it's +2. Yep. It's going to lose both of those s electrons. Yeah.
Thank you.
It's going to lose both of those s electrons. It's going to become a +2 charge. And then we have to say, okay, so X is going to be something that charge balances that. So I'm going to need two things that are going to be opposite charge of +2 that add up to +2. So I'm going to have a negative charge. So it's going to be anything that's in the -1 column. So it's going to be halogens, group 7.
Okay. Well, I put 7A.
Yeah.
Okay.
Question?
On the homework, we
Pretty much
frequently have to
see
like do that many
Plus
problems
two
or like do any problems finding uncertainty using the equation. Do we need to know how to do that?
There are some problems using uncertainty.
That would take
Yeah,
like
there were, but we didn't have to use the like delta x delta v equation rather than that.
Certainly you did.
Yeah.
There were two problems on the homework where you had to do that.
Really?
It was on homework 3.
Oh no, okay, yeah.
So
That's
8,
not-
8, 9.
I was.
Okay, Can you go over the Rydberg equation and like?
Well, let me make sure.
No,
So,
no, I got. Yeah, I was just.
Okay.
Yeah.
Rydberg equation. What about it?
I don't really get the things where it's asking for transitions in energy levels.
So let's go ahead and think for a moment about where the Rydberg equation comes from, right? So we've got some H psi, E psi. The important thing here is it gives us our wave functions, which give us our N, L, M sub L, M sub S, and it gives us our energy. If we're looking particularly at the hydrogen, this is going to be negative Rydberg constant over N squared, right? And then I can start to look at these different energy levels. Again, for hydrogen, and I can look at my N equals 1, I can look at my N equals 2, I can look at my N equals 3, my N equals 4. This is going to be negative Rydberg. This is going to be negative Rydberg over 4, negative Rydberg over 9, negative Rydberg over 16, so on and so forth, going up forever, right? And now what I want to look at is, from our quantum theory, we know that the thing we care about are transitions. This change in energy is going to give us some photon with energy, right? And the way that we think about it is that the change in the energy of the atom is going to be equal to the energy of a photon. And if the atom is losing energy, we're creating a photon with positive energy. And if the atom is gaining energy, we're destroying a photon with positive energy. The photon always has to be positive energy, which is why we toss the absolute value on there. But we still have to have the logic of whether the atom is actually gaining energy or losing energy. If we looked at this and we did it generically, we could then also say the change in energy of the atom is going to be equal to negative Rydberg constant. It's going to be the change in energy between the two. So you notice I'm just using this equation twice. I could put this negative Rydberg constant through, have negative Rydberg over n final squared, so like the energy of the final state minus the energy of the initial state. Because the way that this goes, the final state is always going to have a bigger negative energy than the initial state. So if I'm looking at emission, that is to say when I'm going down, whether I'm looking at the emission to the ground state, so also keep in mind, when we're doing this, like hydrogen gas, if I remember when I held up the lamp that had hydrogen gas, at first it wasn't like glowing, it wasn't doing anything, it was all in the ground state. If you think about those solutions that I sprayed through the fire, if I just spray them in the air, they don't do anything. We need to energetically excite the electrons up to these higher levels, and then see the light that comes out as they relax down. So we're looking at emission.
It's always N sub F too, for visible light.
For visible light, right? So when we were looking at those hydrogen lamps, we were seeing visible light. There was ultraviolet light coming off. There was infrared light coming off. There were dozens and dozens of different wavelengths coming off that we weren't measuring because we didn't have one of the special scopes that could see the different wavelengths. We were just doing visible because we were using our eyeballs or our cameras, right? So this is where we get the Rydberg equation. It's a combination of solving the Schrödinger equation and then this relationship between change in energy and wavelength. Yeah.
How in depth should we know the Schrödinger equation stuff?
That's more than enough, right? Just this kind of definitional idea of the Schrödinger equation takes into account kinetic energy and potential energy and allows us to define functions and energies for a system. That's more than enough. Yeah.
Can you do one of the problems where you like get a wavelength that's emitted and then you know like the final energy level and you have to calculate what it started at?
Sure.
Because I always get that.
Do you have a problem with that?
I could look one up. Like
Look one up real quick.
On the quiz.
Oh, let's do the quiz one.
Okay.
And I think the reason that a lot of people got the quiz one wrong is because this relationship, a lot of people are just saying the energy of the photon equals the energy of the atom. They're forgetting about this absolute value step.
Okay.
And that's actually important. You have to know. There is an equation that I don't like that's specifically for emission. if we wanted to do the one that is the equation, the Rydberg equation specifically for emission, you've got 1 over lambda equals R times 1 over n1 squared minus 1 over n2 squared, where they say n1 has to be greater than n2. Is that right? Wait, let me think about this. Nope, opposite direction. N1 has to be less than N2. So that way, this one is going to be a larger fraction. So if this is like 1 and this is 2, you've got 1 minus a quarter. If this is 2 and this is 9, you've got a quarter minus a ninth. This argument guarantees that this stays positive, so we get a positive wavelength. Notice this argument also guarantees that we have emission, so that you can just essentially know that it's emission, so the change in energy of the atom must be negative, and they just eliminate that negative sign there.
Okay.
So this relationship allows us to eliminate that negative sign there.
And it's a different Rydberg.
The Rydberg constant is different, right?
Okay.
This is going to be in units of inverse meters.
Uh-huh.
It's something like 1.07 or 1.09 times 10 to the positive 7. Something like that. I'd have to look it up to get it right, but it's something on the order of 1 times 10 to the positive 7.
Uh-huh.
This Rydberg constant is in terms of joules, or energy.
Okay.
And it's going to be 2.18 times 10 to the minus 18-ish.
I have 125. Oh, 128.
The reason I like this equation more is it works for absorption or emission, as long as you can think about whether the change in energy of the atom is positive or negative.
Okay.
So if we're told the final and initial, we get the energy change in the atom, and then we say that's going to be the energy of the photon. The place where people mess up is when we do it backwards, and we're like, oh, is this emission or absorption?
Uh-huh.
You don't know if the change in the energy of the atom is positive or negative.
Yeah.
So, did you find the
I don't
problem?
have a quiz with me.
Let's do it.
It says that the wavelength is 109.3.8 nanometers. And then
109.3.8.
and then it says that you should be able to figure out n final equals 3.
Why can we tell n final equals 3? Don't. I mean, can you tell just from this?
No, it says hence since it's an infrared emission. We should
Right.
be able to figure it out.
It's infrared. When we just said earlier, infrareds are n final equals 3. So what's an initial?
That's what we're solving for.
Notice this is the place where that equation in orange would be quite nice. We know that this is emission because the problem says it's emission. We can plug in the wavelength, the funny Rydberg equation, and we can say the n final is going to be n1, because the thing that we know for emission is n final is smaller than n initial, right? Because an emission is always a drop in energy. Conversely, we can do it this way, where we can say that the energy of the photon is equal to 6.626 times 10 to the minus 34 times let's just call it now 2.99 times 10 to the 8 divided by 109.3.8 times 10 to the minus 9. I don't have a calculator, so if you got a calculator, help me out with that.
Isn't that 12?
What?
Nanometer?
No.
Minus 9.
Oh, it's pico? 12?
Pico,
Pico
yeah.
is 12. Okay, my bad.
Extra 10.
Yep.
Wait, what would you use the 1 over lambda equals r?
I don't use it, to be honest. It's on the equations sheet. This would be a good example of where you could use it. You can use it anytime you have a wavelength and you're just looking at emission. It's specifically just for emission.
Well, we don't need to use it. We could just use
No,
the regular
you can just use this one.
It's 1.8, 16 times 10 to the negative 19.
It's going to be in units of joules, and that's a reasonable energy for a photon, right? We expect energy on the order of joules. Now the problem here is the energy of the photon is equal to the absolute value of the energy of the atom. So is the atom gaining or losing energy? If it's emission, it's losing energy. So I can say that the negative energy of the photon is equal to the change in energy of the atom. And that allows me to get rid of that absolute value. That also allows me to just say negative 1.816 times 10 to the minus 19 is equal to Rydberg constant negative 2.18 times 10 to the minus 18 times 1 over 9 minus 1 over n initial squared.
So you make this negative because of the
Because
value.
it's emission, because the absolute value. Because I want the energy of the atom, not the absolute value of the energy of the atom. So I had to do a little logic there. That's the step that most people miss. They see that other Rydberg equation, they think that you can just equate it.
Okay, I think that's right.
But you can also see how this leads to that equation in orange. I get to get rid of the negative sign. That equation in orange doesn't have a negative sign because it's always for emission. You could solve that though, right?
Yeah.
Great. You should get, what is it, 5?
I think it's
6.
6.
5.99.
6.
And then on the equation sheet, there's a z in the Rydberg equation.
Yes.
What is that about?
What is Z?
It's
Not atomic mass, atomic number. That takes into account the nuclear charge and how well the nucleus, because essentially, right, this is an energy argument.
Okay.
So if I had more protons in the nucleus, I'd have more energy of attraction. So the Z allows us to essentially modify the Rydberg equation and take into account other nuclear charges.
Okay.
The reason we haven't seen it is because our calculations for hydrogen, Z is always equal to 1. But if we wanted to start looking at other hydrogen-like atoms, we could start looking at different Z values.
Okay.
Which always gets more complicated real fast. Question?
Yeah, they get more complicated because of like electron repulsion and stuff
Yeah,
like that.
exactly, right? That's the same reason, if you remember earlier when I was saying, oh, these electron configurations there's a lot of exceptions and we're just doing the ground state. The reason there's all those exceptions, that energetic benefit also has to do with electron repulsion versus nuclear attraction, right? The electron repulsion, like the pictures we have for our energy levels, they're all more dynamic than the picture would lead you to believe, because electrons are moving around, they're moving in, they're moving out, they're repelling each other, they're attracting to the nucleus. There's a lot of dynamics in there. On average, they're pretty good though. Yeah.
For the midterm, you're saying like the beginning is the multiple choice short answer, or not short answer, like the
Short free
multiple-
response. Yeah, so sorry, short multiple choice,
Yeah.
long multiple choice free
Yeah.
response.
And you said there's like the short multiple choice is mainly definition.
Definitions and concepts.
And would you say that like any of the ones in the book are for a game, or is it
Yeah.
mainly okay?
Definitions, concepts, like, hey, what about like the problem we did earlier where it's like ionization energy, electron affinity, electronegativity, like how do these relate to each other?
Okay.
You say an atom with a high ionization energy will also have a high blank. And it'd be electron affinity or electronegativity would both be reasonable answers.
And then the free response questions, are those calculations or is that also conceptual?
Yes. Both.
Both, okay.
Both. Trying to put it all together and make you think beyond what, like, so the real thing is and it really gets down to kind of like pedagogical theory of like, what is the purpose of all of this, right? And ideally what I would do is I would write 4 free response questions and you would answer these questions and I just see how you conceptually process all of the things we've learned and extrapolate it to other ideas. That would be great. That test would take a while, not only for you to do, but for me to grade. And so I kind of compromise with like, we'll do some multiple choice questions to get some base understanding and make sure that you've got the simple concepts going and it's quick for me to grade. But like I still feel like I need to do a free response section so you can show that conceptual understanding and that kind of relation between the calculations and the concepts as well. It's really hard to do relations between calculations and concepts in multiple choice. So that's where the free response comes in. Ironically, oh, now I'm going to get sidetracked. Let's talk other questions. Yeah.
About lattices, what do you think we need, or like what would you say like we need to know the most? Like structures, like the FCC, simple cubic.
Simple cubic, body center cubic, face center cubic.
Okay, and like that charge would charge increases the lattice energy. The higher
Yeah,
the charge,
that
and then a lower
relation
radius
between charge
increases.
and lattice energy.
Would you say like that's like about the scope of things we need to know? Because like some of the questions you were doing on the board seemed like way like past like what we've gone over.
Coordination number.
Okay.
Lattice energy, number of atoms in a unit cell, volume of a unit cell. For the simple ones, not for the complicated one.
Wait.
Um,
Can you do what finding the volume of a unit cell? Is that just the? Never mind. Can't figure it
it's
out.
not. Yeah,
Question
it's
something
it's
out
it's on the equation sheet, and it's just it gives you the side length. You just cube the side length. I can't think of.
Yeah. How do you
think
find the
it's
side length again?
It's on the equation sheet.
Oh, okay.
It's a simple.
For the three simple ones, it's on the equation sheet, and it's trigonometry. Question.
Could you explain coordination numbers again?
Coordination numbers is the nearest neighbors. So if we looked at an atom, we want to say, okay, which atoms are close to that atom? This gives us some information about what interactions are happening. It's going to give us some information if we take ratios of coordination numbers. It's going to give us ratios of the atoms in the compounds. When we're looking at our metals, we're looking at how many nearest neighbors it's interacting with. When we're looking at our ionic solids, the more complicated ones, we're going to be able to figure out the ratio of cations to anions, because the cations will always have anions as their nearest neighbors. The anions will always have cations as their nearest neighbors. So we'll be able to figure out like what the ratio is. Is that good enough?
Yeah,
Yeah.
I also have another question.
Yeah.
Could you explain like how like black body radiation got to like the photoelectric effect? Like,
Oh, they are two completely
Yeah.
separate phenomena.
yeah.
They are
Explain
two
them.
different things. So black body radiation, we just really did definitionally, and we're like, hey, that's weird. People couldn't explain it until Maxwell Planck came around and said, hey, let me do this weird thing that says energy is quantized and I can explain it. And that was all we did with black body radiation, was say that was the first experiment that was the first example of an experiment or a phenomena that was explained with quantum mechanics that fixed problems of classical physics. And then the photoelectric effect was the second-ish experiment. I don't know the exact timeline of when these experiments were explained, but the photoelectric effect was a pretty big deal too. I mean, Einstein is the person who did it, got a Nobel Prize for it. Everyone thinks it's the E equals mc squared thing, but no, his theory of relativity, no, it was the photoelectric effect was the one that he got a Nobel Prize for. I think you only get one. I feel like he would have gotten two if somebody could get two. I don't know if he got more than one. But in any case, the photoelectric effect is an actual we did calculations with that. We did the description of the kinetic energy of the electron being released related to the energy of the photon that's hitting it versus the energy with which the metal's holding on to the electrons, right? And it's kind of that balance of how well does the metal hold electrons versus how much energy are you hitting it with. And that's why you had the energy of the photon minus the energy, the work function, the energy of the metal's holding onto the electron. But that one we did calculations, and they're two completely separate experiments. Yeah.
How would you find coordination number like without physically like seeing like what it?
Two options. You would have to see it.
Yeah.
Or like I don't know if I was just like, hey, what's the coordination number for like a gold crystal?
Yeah. Okay, because I was like, I don't know.
I don't think you could do that.
Okay.
If I told you the crystal structure and you happen to memorize the coordination numbers for the three different ones, what is it? It's 6, 4, 12. No, 6, 8, 12. You're right. 6, 8, 12. Like if you just happen to memorize that, great. Since I'm not a big fan of memorization, I'd probably show you the crystal structure as well.
Okay.
And be like, for this crystal structure, which happens to be the crystal structure of gold, what's the coordination number of every gold atom? Yeah.
How would you find lattice energy? Because I've looked on the worksheet, it doesn't specifically say.
So we don't explicitly find lattice energy. If we wanted to explicitly find lattice energy, you do that in 125. How many of you are taking 125? So a couple of you you're going to do the calculations that lead up to finding lattice energy, where you take into account the enthalpy of formation for different compounds. However, for us, we're not explicitly calculating lattice energy. We just have the qualitative trend which relates lattice energy. So if I gave you two crystal structures, you could say which one's bigger, which one's smaller.
And it's just the charge and
Charge and
the radius.
inverse of radius.
What do we need to know about like bands and gaps and that kind of stuff?
That's not going to be on this midterm. That'll be on the
Okay.
next midterm. And I'll probably revisit a lot of this crystal structure stuff on the next midterm because I'm realizing I didn't ask enough questions about it. I'm like, oh, I should have asked so many more. Yeah.
So for mass of a unit cell again, so you do like for that selenium,
The zinc selenide.
yeah. So like it would be 4 for both of them. So what would you multiply by? So like 4 times what?
4 times the mass of zinc plus 4 times the mass of selenium.
Oh, so
leave
just
it in
the
AMU.
Yeah, and that gives you an AMU. And then you can multiply, you can do the unit conversion between AMU and kilograms if it asks you for the mass in kilograms.
Oh wait, but the AMU is also so you would multiply basically by the atomic mass on the periodic table.
Yes.
Okay.
Yeah.
Like, why would you do 4? Is there like a specific?
So that was because of the particular crystal structure and the number of atoms in that
Oh, okay.
crystal structure. I think you weren't here for that one. Is anyone asking questions online? Is anyone watching? No one's watching. I'm gonna go ahead and stop this video. That's me. It counts me as watching. So I think we're starting to repeat questions, so I'm just gonna go ahead and stop this.